So, good evening, all. Today we'll be continuing with the week 6 problem solving section of engineering hydrology class. So, basically, in the previous weeks, we started off with the hydrological cycle, different components of the hydrological cycle, and different processes involved in the hydrological cycle. And then we started looking into each of the processes and how they can be modeled or they can be quantified. And for modeling these processes, we had been using a theorem that is called the Reynolds transport theorem. Basically, that particular theorem was helping us to apply these laws of motions, which are derived in the Lagrangian or point uh, frame of reference, and to apply to the fluid systems, which have extensively been derived or quantified in the volumetric frame of reference or the Eulerian frame of reference. And in the previous lectures, we have already seen the processes related to the atmospheric water. Then we came to the subsurface where we dealt with the soil moisture. The process in the main process is that the infiltration processes. And in the atmosphere, we have seen the main processes, which are the precipitation, evapotranspiration, and condensation. So next, in this particular week, that is week 6, we'll be looking into the surface water. That is basically the precipitation that falls on the earth. As you know, it will be basically would you say it will be basically distributed like the once it reaches the earth, some of the water get evaporated, and we already have covered that. And then some water gets infiltrated to the subsurface, that also we have seen in the previous lectures. And the remaining water, after satisfying the evaporation and the infiltration demand, and once the ponding starts, that is ponding also we saw in the previous lecture, when the soil gets saturated, the water starts gets ponding, and these ponded water starts flowing. So this particular flow of water on the Earth's surface is called the surface water flow. So in this particular section, we will be focusing on surface water flow, right? So before starting, I will give a brief introduction of myself. So I'm Akhil. I'm working as a PhD scholar in IIT Delhi. I'm currently in my fourth year of my PhD. I have done my BTech from NIT Calicut in the discipline civil engineering discipline, and then I have completed my MTech from IIT Guwahati. I worked under the supervision of Professor Srija Pekat, and currently I'm enrolled in for my PhD in IIT Delhi from the year 2022. So we'll start with the problem solving section. So for those who are attending for the first time, the pattern which I follow is I've selected six MCQ questions and six NAT questions, that is numerical answer type questions. And the MCQ questions are selected in such a way it will cover the entire concept which have been taken in the week 6. So all the main concepts will be covered. It would be like a recap for you. And the numerical answer type you will be have it will be like a practice for you to solve the how we can solve the questions related to these concepts which are saying the MCQ question. And also some of the questions which are like due to the limitation of the time, some of the numericals may not be able to be solved in the lectures of NPTEL lectures, so that we'll be solving for today. Right. So we can start with the first question. So the first question, it's a multiple choice type. That is, according to the surface water storage concept, what type of storage is held for long period of time and primarily depleted by evaporation, such as soil moisture storage? So it is basically talking about storages, right? So they are asking, is talking about the concept of surface water storage and what type of storage can hold water, what type of storage can hold water for a long period of time and primarily depleted by evaporations and such as soil moisture storage. So they have also given the example what the soil moisture storage storages like soil moisture storages are called, which can be depleted only by the processes like evapotranspiration and which can be held for a long period of time. So we already saw in the previous lecture what is soil moisture, how the water is getting stored in the unsaturated zone of the subsurface, right? So we need to know the concept of water, surface water storages, and we need to understand what are the different types of storages, the ones which holds water for a long period and ones which holds water for a short period, right? So before starting to the main questions, I'll give you a brief about the surface water. So the topic that we are going to deal today is called surface water. Surface water, we already saw subsurface. Now we are going to the surface. And in while during this section, so I'll be using a term catchment or watershed. So it has been already explained to you in the very first week lecture. So I'll give you once more, I will explain that. So that particular we'll be whenever we talk about surface water, we'll be need a reference area or the area under like a control volume concept. Like we'll be taking a representative area where we'll be calculating these surface water, quantifying surface water terms. Okay, so that is called a catchment. So what is a catchment? uh, we'll be explaining here. So a catchment, or it is also called watershed. So you may be already knowing if you have seen the previous lectures. It's an area of land draining into a into an outlet. So basically, it is draining to a single outlet, right? For example, it can be a stream at a given location. So this is basically the definition of a catchment or a watershed. Right. So basically, what it represents is whenever we take a bay, watershed, or it is or a catchment, it will be looking something like this. So this I am calling as an outlet point. So within that catchment, there will be a main stream and there will be substreams or tributaries. We call this, right? So these will be meeting to a single outlet point. So the rain that happens, the rain that falls into this catchment will be flowing to these substreams which are joining the main stream, and it will go to a single outlet point. So this is called a catchment area. And also if a rain happens falls outside this catchment, it will be flowing to the another catchment, right? So here along this line, so this particular boundary is called a ridge. Ridge means it has the surrounding points. Compared to surrounding points, this particular boundary has a higher elevation. So whatever the rain that falls within that boundary will be flowing to the catchment. So this can be a representative area which we are analyzing. So whatever, so in the very first module also we saw how to write a water balance for a catchment. So it is, so precipitation is the main input. Then we have the losses like evaporation will be happening, and we have losses like infiltration, that is water that is infiltrating to the subsurface. Then it will be followed, then whatever there will be abstraction losses. So that we'll be dealing in detail in the coming questions. That is, water gets, this is abstraction that I'm denoting it by A. That is when the water reaches, before reaching the catchment, it gets stored in the canopy or the canopy storage. The canopy storage. Canopy means in the branches of trees, the leaves. The water get intercepted before it reaches the catchment. So some water is lost in that way, and also there will be depressions that are happening that will be there in the land surface. Some water will be stored in the depressions. So that all are incorporated in this particular abstraction, initial abstraction we call it. and finally whatever is left will be forming as runoff. Right, so runoff is the water flowing over the surface. That will be equal to, so this is the input minus output. So input is precipitation, these all are output, so we can put it all together. If these all are output from the catchment, that will be equal to the change in storage, right? So this is about the catchment. So we need to have an idea about this before we moving to the further questions. And the concept of surface water. So how we define is surface water is nothing but water stored or flowing on the Earth's surface. The water that is getting stored and flowing in the Earth's surface, not the subsurface. In the Earth's surface, it is called the surface water, right? So the main important why surface water is so important is that surface water is in constant is continuously interacting with interacting with so it is continuously interacting with the atmosphere and subsurface, right? So it is continuously in touch with the atmosphere and the subsurface, right? So there are two feedbacks happening. So if you take this as surface water, surface of the earth, so the surface water here, surface water, it is atmospheric water. This is the subsurface water. So this particular uh, surface water is in constant touch with the subsurface and the atmospheric water. That's why it is very much important to understand this, right? And so, just a minute. So now we can come to the question. So you know what is surface water, what is a catchment, that is clear to you. Now we can see how the surface water is also that we saw the definition is the component of the water that is getting stored and also that is flowing on the earth's surface. That is called surface water, right? So what are the different types of storages, water storage and surface? That we'll be seeing here. So during a storm, the precipitation that comes to the surface gets stored, and these storages can be of two types. So two types of storages are there. The first one is the retention storage. The second type is the here. Second is the detention storage. So the two types of storages in the surface water is retention storage and retention storage. Right. So the so retention storage is nothing but storage held for a long period of time and depleted by evaporation. So that is what our question asks, right? So the storage is held for a long period of time and depleted by evaporation. And the example is soil moisture. So these are the type of storages that are coming out of a storm water that can be held for a long period of time. So for example, soil moisture can be held for a long period of time, right? And they are depleted by processes like evaporation, evapotranspiration. So so we can look into what is a detention storage also. So it is the opposite of that, that is short term storage. short-term storage and depleted either by evaporation, similar to our retention storage, or outflow away from the storage location. So these detention storage, so what do you mean by this retention storage? For example, is flood control ponds. So basically, these retention storage, they are nothing. They are they're short-term storages. So the purpose of them is when if you are seen in the urban areas due to these sudden high intensity rainfalls like cloudburst, the urban areas get flooded very quickly, right? So there's one of the flood control technique that has been highly implemented in urban areas is that near to these highly flooding areas, we will find a location and we'll be making a storage structure like a reservoir or we'll be like we can say it is a large pit we'll be taking and we'll be sealing it with concrete and then we'll be directing the water to uh, uh, that particular storage structure. So what happens is that instead of water getting flooded in the urban area, the water gets stored in this particular tank. So whatever the water is coming, that will be stored in the particular tank, and at the bottom of the tank, there will be. So if I want to show you a structure of this tank, so this will be our ground level and this particular area was getting flooded. So we will direct the flooding water to this particular tank and this tank gets filled up. So there will be an outlet at the bottom of the tank that will be releasing the water at a rate Q that will be a very slow rate. And so what the purpose of this tank is, it will actually when the high intensity rainfall comes it will reduce the ponding effect, right? So some water gets stored, like in buffer, it can act. It can hold some water, but and release it in a very small rate so that the flooding won't occur, right? So that is one of a type of a flood control technique that is being implemented in urban areas. So such a tank where the water, surface water, they are stored for a short period that is called detention storage. So this is also called a detention storage tank, right? And so here the losses can be the water in the tank gets evaporated by evaporation and it gets outflow. This is outflow that happens away from the storage location, right? So this is one of a way, like if the drainage system there cannot be expanded, or if even if we expand the drainage system, the water is not being what we say the peak runoff or the peak flooding happening is not decreasing. Then we can go for such techniques which are extensively used in urban areas to control urban floods. Right. So these storages are called detention storages, which will store water for a temporary storage of water and unlike the retention storage which can store water for a long period of time, right? So the options you can see, so the question is about the storage which can store water uh, for a longer period of time, so that is called retention storage, right? So detention storage is nothing but we can store for a short period of time. Interception is nothing but the water getting trapped before reaching the surface. So before reaching the catchment or the surface, water get intercepted between the rainwater get intercepted between. It can be stored in the leaves or the branches. So that are called interception water. So they are not long term. So can also store water for a small period and depression storage is also when rainfall occurs, there will be small depressions in the surface, right? So water gets stored in the surface. So that is also temporary. After some time, when the rain recedes, either they will flow out or by evaporation they get emptied. So ones which can retain water, store water, and that can be used further for the human purposes, they are called the retention storages. Groundwater is also a retention storage, right? And also the dam, the reservoir that we built to collect water, so that is also a retention storage because we are retaining water for a long period of time. So we can now come to the second question. So the second question is, how does saturation overland flow differ from the Hortonian overland flow? So here we need to know about a concept of what is overland flow. That is one thing, and then we can come to what is saturation overland flow and what is Hortonian overland flow. Right. So basically, when the rainfall happens, so we are saying rainfall is happening, and rainfall of P is happening. So we saw the water budget. So initially, the water gets infiltrated, right? So there will be before that, before infiltration take place, before the water reaches the surface, there will be interception and evapotranspiration happening, right? So water will be interception losses will be there, and then we have the evapotranspiration happening. Okay, so this is the two couple of losses, and once after these two losses, then uh, what comes is that if you look into the storages, then whatever left from this will be stored as surface water storage. Like this is called surface water storage. Whatever left from this will be stored as surface water storage. And another storage component is the groundwater storage, right? And another component will be unsaturated unsaturated water storage, that is soil moisture storage. So these three storages will be satisfied with the this some particular amount when by subtracting infiltration, interception, and evapotranspiration. Right. So once when we see the groundwater storage part, we saw groundwater will be flowing to the flows to the streams, and this process was called, we already saw it is as base flow, right? There's a flow happening from groundwater to the streams, that is called base flow. In the unsaturated zone also, there's a flow happening along the surface to the streams, that is called interflow. That is flow in the unsaturated zone or interflow. And then we have flow from the surface to the streams. So that is called an overland flow. So that is the three types of flow that happens. So the precipitation occurs, then it will be intercepted, and then evapotranspiration takes place. Whatever the water remains will be stored in the surface water, in the surface, then the groundwater, and the unsaturated zone water, unsaturated, unsaturated water. Like there are three types of storages. So within each of the storage, it will be flowing to the streams. There are the stream networks. Streams you already saw in the sketch. It will be flowing to the streams by three types of flows. That is base flow for groundwater, interflow for surface water, and overland flow. So overland flow is nothing but that is just like a sheet flow. It's just like a sheet flow. The water that falls on the surface when the soil gets saturated, it flows as a sheet flow, and once with a what we guess like the sheet flow means it will have a thin layer, the thickness will be thickness or the depth will be less, and it will be spread over an area. After some time, they get narrowed and forms the streams, right? So that is called an overland flow. So overland flow is clear to you. It's nothing but a sheet flow that occurs just after precipitation or a storm. So and this will be spreading, and then it will narrow down and forms the stream flows. Right. So in this question, they're asked about two types of overland flow, that is saturation overland flow and the Hortonian overland. What is saturation sheet flows and the Hortonian Hotonian sheet flows. Okay, so we will see both. So the first one is Hotonian overland flow, right? So Hotonian overland flow is nothing but the catchment is saturated from the top, right? So if I could explain this with a diagram, so if you have seen the lecture, it would be clear to you. Like we take a hill slope and we have a stream at the bottom. So this has a water here, and let us consider rainfall is happening over in this particular stream. So what we said about this is the uh, it is saturated from the top, right? So the catchment is saturated. So this is a take a, is a catchment. So the catchment is saturated from top. From top, the catchment is getting saturated. So the rainfall is happening, and when the intensity of rainfall, so intensity I'm representing by I, is greater than the infiltration capacity FP. So what happens is that here the near surface, the subsurface near to the surface gets saturated. So this will be, so this particular zone, or I could highlight using this particular zone surface near to the surface first gets saturated. So below this it will be unsaturated as the rainfall in intensity is very high of rainfall is very high compared to the saturation capacity of the soil. This particular layer gets saturated. So once these layers get saturated, what happens is that water gets ponded and it flows along the slopes. So along the terrain slope, water gets ponded and it starts flowing and meets the river. So this kind of, so this is actually a sheet flow that is happening, right? So it has a width. It will be spread along a width, right? And this particular sheet flow that is happening is called Hortonian overland flow, right? So basically here the water was getting saturated, the catchment was saturated from the top and the bottom, then it moves to the bottom, right? So that is the main uh, property of a Hortonian overland flow. So next is a saturated Hortonian flow. Saturated overland flow. So with the same diagram, if there is a hill plane that is at the top of the hill, and we have the terrain and we have the stream, right? And we have water at this particular level, and take a case where the in the upstream or the uphill rainfall is happening. And what happens here is that due to this rainfall, infiltration will be happening and this particular zone gets saturated. That is the uh, just below uh, the uphill, just below there that get saturated, right? And this entire area gets saturated. And after getting saturated, what happens is that interflow starts happening. So, so interflow we already saw, that is the flow in the subsurface region towards the stream following the along the surface path. So the interflow starts happening. So there is a subsurface flow that goes and meets the streams. So when interflow happens, when here the interflow is happening or meeting the stream, here surface, this is the Hortonian overland flow. Interflow is happening, and at that time, if a rainfall happens here in the downstream region, if rainfall starts happening here, so the layer below this here, so this area is already saturated, right? It's already saturated. You has the water has the uphill got saturated and the interflow has already begun. So then what happens is that whatever water falls here will flow as a overland flow or a sheet flow and goes joins the stream. And this particular flow or the overland flow or sheet flow, this particular overland flow is called a saturated overland flow. Right. So this is produced when the subsurface saturates the soil near the bottom of the slope and overland flow occurs as the rain falls on the saturated soil. So rain happened, it saturated the soil below, and then again when the rain happens in the bottom, then overland flow occurs. Right. And this flow will occur uh, basically occurs in the hilly areas where interflow occurs. So this is called interflow. This is called saturated overland flow, and they most often occurs at the bottom of hill slopes and near stream banks. So they occur. So as you can see from the figure, this is the bottom. They occurs at bottom of hill slopes and near stream banks. So that is water is saturated from the bottom here, right? It's not getting saturated from the top. So now we can come back to the question. How does saturated overland flow differ from Hortonian overland flow? So we can see the options. Saturated overland flow occurs when soil is saturated from the above by the rainfall intensity. So that is nothing but a uh, definition of Hortonian overland flow, right? So this is wrong. Saturation overland flow occurs when the soil saturated from below by the subsurface flow. Right, so that is the correct option, right? So subsurface flow is also called interflow. This is nothing but interflow. So when this occurs, saturation overland flow occurs, right? So that is the correct option. Then Hortonian overland flow occurs at the bottom of the hill slopes. Actually, saturation overland flow occurs the bottom of the. So this is a wrong statement. Hortonian overland flow is saturated from below by interflow. That is also wrong, right? So the correct answer is saturation overland flow occurs when the soil is saturated from below by the subsurface flow. Okay. So now two types of what is overland flow is clear and two types of overland flow, that is saturated overland flow and Hortonian overland flow is clear to you. Now we can move to the third question that is related to how we quantify runoff. So we saw in the previous lectures how we quantify precipitation, how we quantify evapotranspiration, how we quantify infiltration. Similarly, there are techniques used to quantify runoff or surface water flow. So one such method is called the SCS method, or it is also called SCS curve number method. So the questions related to this, in SCS method of abstractions, the curve number is defined within a range. So there is something called a curve number. We'll be saying it while solving this question. The curve number is defined in a range of 0 to 100, right? So what does the curve number 100 represent? Okay, so that is the question. We need to know what is SCS curve number method, and then we need to understand what is curve number. And so all these details we need to conceptually saying by solving this particular question. Okay, so let's start with SCS method, and this method is used for quantifying the abstractions. That is, from the precipitation, we know how much is evaporated, we know how much is infiltrated, and we know how much. So these two quantity we already know because we in the previous lectures we have already seen how these are quantified, right? So in this particular lecture, we will be seeing whatever is left, that is whatever one more loss that is there. If we detect that, we'll be getting our runoff, right? So that loss is abstraction losses. So if we get this particular abstraction loss, then whatever if we subtract, we'll be getting our runoff or excess rainfall excess. So that so this particular method was defined or was used to find the abstraction losses so that we can uh, find or quantify the runoff or the rainfall excess. So SCS stands for Soil Conservation Service. It was developed in 1972 to compute. So basically to compute abstractions from storm. So a storm will occur. If we get the abstraction, we have the other quantities, so we can get the rainfall excess, right? So there are two assumptions. The first assumption is assumptions related to SCS method. The first one is the depth of excess precipitation. So the excess precipitation, PE. So excess precipitation is nothing but is called runoff. Excess precipitation is nothing but runoff. Okay, so this term we'll be using excess, whatever the rainfall excess is there by its technologist also, this is also called runoff, will be less than or equal to the depth of precipitation, P. So this is obvious, right? So whatever the excess runoff is happening will be less than or equal to precipitation. So if there are no losses, they will be equal, right? They cannot be greater than. So that is one thing. And second thing is when runoff begins, uh, depth of water retained in the watershed. Depth of water retained in watershed or catchment will be less than or equal to, that is, we are calling it as FA, will be less than or equal to potential maximum retention. So we saw what is a retention storage, right? So retention storage is nothing but water can be stored for a long period of time, right? So the maximum retention storage for each catchment will be having a maximum retention storage. And the depth of water, and what this particular assumption is that when the runoff begins, at the time when the runoff begins, the water that is retained in the watershed can be stored in the watershed will be less than the maximum potential it can retain. So in another way we can say that only when the maximum potential is reached, then the runoff starts. That is another way of putting this. Okay, so these are the two assumptions associated with it, and you need to see a fundamental hypothesis. So the fundamental hypothesis is that so whenever we derive something or we will be having a hypothesis, right? We will be testing this particular hypothesis whether it is correct or not. So in this case, the hypothesis, just a minute. Uh, in this case, our hypothesis, fundamental hypothesis is that the ratio of actual retention, that is actual retention of rainfall to the potential retention Potential is nothing but maximum, is equal to the ratio of direct runoff to the potential rainfall minus initial abstraction. So if I could put it in words, in mathematical terms, we can say FA, that is actual retention, yeah, of the catchment by the maximum potential retention is equal to the potential rainfall PE divided by the potential rainfall, no, that is the rainfall excess. P is rainfall excess divided by potential rainfall P, that is maximum rainfall, minus IA. So this is the hypothesis. This hypothesis they have proved it correct. This particular team, that is SCS soil conservation, that they have proved this particular hypothesis correct. So this particular method has been derived based on this particular hypothesis. So when we use this particular equation, further solve this, and we have this particular relation, and also we'll be having the continuity equation. So that is nothing but total precipitation is equal to runoff plus the abstraction losses plus the infiltration losses. Right. So this particular technique considers the infiltration also. This is the continuity equation. If we combine these two, if these two we combine, we'll be getting a expression for the uh, rainfall excess or direct runoff. So that is equal to P minus IA, the whole square, divided by P minus IA minus or plus S. So this is the equation for direct runoff we are getting based on the SCS method by applying this particular hypothesis, which they proved it correct, and this particular continuity equation, right? And finally, we derive this, and then what we are doing some adjustments, like initial abstraction IA is equal to 0.2 times the maximum retention storage. So this we got it experimentally. Experiments, they conducted a lot of experiments, they found this relation. And finally, we have the relation for PE as P minus 0.2 S, the whole square, divided by P plus 0.8 S. So this is the relation for rainfall excess using what we call the SCS method. Basically, we have incorporated infiltration, and also we have incorporated the infiltration and initial abstraction. Sorry. These two terms we have incorporated, and we have come out with an expression for rainfall excess. Right. So we got the expression. So here precipitation we can get. The next the problem is we how to get this specific retention, how the maximum water that can be retained or stored as retention storage for the catchment, how we can get it. So from the definition itself, this will be a property of the catchment, right? Depends on the property of the catchment, right? So we need to derive this. So this will be a property of the catchment. That is property in the sense it will depend on uh, the vegetation, and it will depend on the soil, soil type, and it will also depend on the land use, land cover. land use, land cover. So these are different, it depends on all these, right? So to define this, they introduced something called curve number, Cn. So the relation the SCS have found that they found is CS curve number Cn. Uh, what they did is basically what SCS did was they basically found S as a function of this curve number. Empirically, they found this, and S is equal to 25400 by curve number minus 254 if you want S in mm, retention in max retention in nm, or it is equal to S is equal to 1000 by Cn minus 10 if you want S in inches. This is the relation they found out for curve number, right? So, so this particular curve number depends on number of factors. One is soil characteristics. So for different soil groups, so they are made in different groups. So that is, they have defined soil characteristics in group A, group group A, group B, and group C. And for each of the group, we'll be having each different curve number. And also another thing, curve number depend is one is soil characteristics that we already saw. The next thing is the land use. So land use can be cultivated land. So for each cultivated land, it can have a particular type of particular curve number. And then we have forest land and wasteland. So there are many other like urban, how much areas impervious that we'll be seeing in a one particular NAT question that in this particular section. And fine, and also it depends on another thing. It is depend is the antecedent moisture content. That is AMC. That is antecedent moisture. So there are three AMC groups. That is group one, group two, and group three. And we are they have given importance to the uh, so they have defined this based on the total rainfall in 5 previous days. So that on the basis of that, they have made it defined into three groups, and within the group, they have made another classification whether we are considering that in the dormant season or growing season. Dormant season is then when the plant growth, the cultivation not taking place, the water demand will be less, and the growing season is when the water demand is high. That is why the Soil Conservation Service they derived this particular equation or this particular technique, especially for estimating the runoff in case of agricultural land or estimation of abstraction losses in case of an agricultural land. So these are the different period or stages of growth, period of time, whether it is in the dormant stage or in the growing stage, right? So for each we have different values different conditions, that is how much rainfall, that is previous 5 days are there, different limits are there, and then we classify into three AMC groups, and each of the group will be having a different CN number, right? So that is how we get the CN number. There are standard tables. The one of the table will be showing in this particular session, and there are also standard graphs through from which we can derive this. Okay, so there are different curves, and from that curves or the from standard graphs we can derive CN number. Once we get CN, we can substitute it here. We will be getting the specific retention. So once we have the specific retention and also we have the rainfall of the catchment, we will be able to find the rainfall excess by the help of the SCS curve number method. Okay, so now we can come to the question, that is, in SCS method for abstractions, the curve number is defined within the range 0 to 100. What does the curve number 100 represent? So basically, uh, there is one more thing which we want to see in this particular about curve number. That is, so based on this, they have derived, as I said, SCS curves they have derived, and so there the CN is defined as 1000 plus 10 plus S. That is, we put uh, the CN, that is by plotting the graph between P versus PE in the site. They have defined the graphs or standard charts, that is P and PE, and there are different relations here in this way, and each are for different curve numbers. So this is for curve number 100, this is for curve number 85, 80, so on, right? So here, if we find the what it is, if we find the precipitation X, if we measure the PE at the outlet, the runoff that is happening in the outlet for this particular precipitation, then whichever the curve number it meets, so these two values we got from the side, and whichever the graph it means, so that is a curve number, right? So that we can put it here and we will be getting the specific retention. Okay, so here this particular curve number uh, falls between 0 less than or equal to Cn less than or equal to 100, right? So that is the question they're asked, when the Cn is equal to 100, what is the, so for each curve number, we the this particular relation holds, and the question they have been asked, for curve number equal to 100, what it represents. So when curve number can be equal to 100, the curve number is equal to 100 when specific retention is equal to 0, right? Then we will be getting 1000 by 10, that equal to 100, right? So it is when that case when specific retention is equal to 0. So specific retention equal to 0 means no storage, can be no water can be stored in that particular catchment, right? So we can see an option where no water is getting stored in the catchment. So that is first one. The first option is completely dry natural surface. So that is wrong. Then completely highly permeable sandy soil. No. Impermeable water surface. Yes. So there the water impermeable surface they cannot store much water, right? A surface with maximum retention. No. So we can take the other extreme case also. So curve number is 100 for a impervious surface which has retention equal to 0. And if we take the other case, that is when curve number is 0, so curve number can be 0, Cn will be 0, when S is very large. The curve number can be 0 when X, this is very large, and it will be in the for the category of very high permeable soil, permeable or very high storage soil, right? So for an impermeable surface, Cn is equal to 0, and for any other surface, natural surface, Cn will be less than 100. So it will lie between 0 and 100. Okay, so we can move on to the next question. So that is, in the analysis of overland flow, the momentum equation used to determine the average velocity is derived based on which specific set of flow assumptions. So this is a question related to the derivation of the overland flow. How the overland flow will, so we saw the derivation, how we derive these hydrological processes in the previous two lectures. So we saw we'll be using previous lectures, we'll be using the RTT theorem, that is Reynolds transport theorem, to derive these expressions. So we'll be applying this for the mass conservation and also the momentum conservation. Then we'll be coming up with the relation or the equation that can be used to model this particular process. Similarly, to model the overland flow process, what are uh, the momentum equation used? What is the momentum equation used and used to determine the average velocity based on the specific set of flow assumptions? So, what are the flow assumptions that are set before we derive the momentum equation for modeling the overland flow? That is the question. So, we need to know the assumptions that are taken while deriving the momentum equation, right? So let's quickly go through two things. That is the through conservation. That is the continuity, mass conservation, and the momentum conservation for the overland flow. So basically, you all already know we'll be applying RTT. So RTT, it will be clear to you. dB by dt, mass rate of change of the extrinsic property of the system. The system is given by d by dt of rate of change over the integral over the control volume, beta, that is intensity property, rho dv, v is velocity, ev is volume here, plus the surface integral of across the control surface, beta rho v, this is velocity, is a vector, and dot da, which is also a vector, right? So this is the RTT. So this is very much familiar to you. So let's quickly see the continuity equation. So the continuity equation, you know, extrinsic property beta is mass m. So dB by dt will be 0. And here also mass won't be beta will be equal to dB by dt, that will be equal to 1. And the assumption that we make in the continuity equation is that this assumption 1, the flow is steady. What this means is that the precipitation occurs, the water gets bonded, and then it starts flowing, right? After enough time after the precipitation, this flow becomes steady. So that is, the water will be flowing at a rate, the depth of water won't be changing with time. So after some time, after enough time after precipitation occurs, the flow becomes steady. So in that case, second term can be also equal to 0 because there is a d by dt is coming, right? So d by dt, control volume, beta rho dv is also equal to 0. So we got this particular term has 0 and also this particular term has 0. Whatever is remaining is control across the control surface, beta rho v dot dA, and beta is 1 and is equal to 0. So beta is 1, density is constant for incompressible flow we are taking. The density we can take it out and it get cancelled. So it will be surface integral rho dot dA equal to 0. This is the continuity equation, right? So in the continuity equation, so now let us see how the control volume is taken in the case of an overland flow. So overland flow, you already know it is a flow of a sheet. It is like a sheet flow. So take a example where this is the terrain and uh, the flat terrain, flat inclined terrain, and the angle of inclination is theta. So we take this particular angle as theta, and here we consider the x and y axis along the inclination, right? So that is one thing we took while we're deriving. Y is in this perpendicular to the inclination and x is along the inclination. And we consider length L. So this particular length, if we are taking, so this length is L, and vertical to that we are considering the control volume. We are taking a control volume vertical to that. So this is our control volume, and along the surface, the vertical surface horizontally, we have our overland flow. So this is the overland flow, water table depth, and the flow is well taking along the inclined surface, right? So the velocity in this is parallel to the inclined surface, right? So we have the rainfall happening at intensity high, and we have the infiltration happening at the bottom at a rate F. So we have rainfall and infiltration. So this is the control volume that we consider to uh, derive for the overland flow, right? So this term is nothing but in words we can say net outflow across the control surface, the control surface. So that is inflow minus outflow, right? So that is equal to inflow minus outflow. So inflow is nothing but precipitation I, but here the I is a rate, and if we multiply it with the area, will be A is in centimeter per hour, right? If we multiply it with the area, we'll be getting the volume. That is volumetric flux. So I into area E will be L in the horizontal direction will be L cos theta, and the width I am taking it as unit width I am considering. The width of the flow, outline flow as unity. And so that is the inflow, and outflow will be, there are two outflow. One is FL cos theta into 1, and we have the outflow, the overland flow. That is also an outflow from the system, right? So that velocity we have, and if we consider the depth of flow as y, so depth of flow, I'm taking this is the y, so this will be velocity into depth into the unit width will be giving us the outflow, right? So the net outflow will be given by if you take the difference, sin replace I, that is I minus f L cos theta is equal to V into Y, right? So V into Y is nothing but our the flux or the overland flow flux, that is Q naught will be equal to I minus F L naught cos theta. So this is the continuity equation. This is how we derive the continuity equation for the case of a overland or for overland flow occurring, right? So next we can move to the momentum equation. So momentum equation, so here we make some assumptions. The assumption that we made in the continuity equation was it is a steady flow, right? So in momentum equation we make use the concepts of of fluid mechanics, and we assume the overland flow has a fully developed laminar flow down a inclined plane surface. So momentum equation, so the assumption is that we take it as a fully developed laminar flow down an inclined surface. So that is the assumption. So we are taking the flow, the overland flow as a fully developed laminar flow that is happening. And for such cases, for laminar, fully developed laminar flow, we have now the equation for fluid mechanics. Velocity is given by rho g sine theta y square by 3 divided by mu, or rho by mu is viscosity, so we can write V is equal to g sine theta y square by 3 by nu. It is kinematic viscosity. And for uniform flow, also for uniform flow, another assumption is that the flow is uniform flow, that is flow depth is not changing spatially, so velocity will be given by g s naught y square by 3 nu. Okay, so it's not is nothing but sine theta. So this is the uh, relation for the overland flow, and using this particular relation we'll be deriving the velocity for overland flow, and then we'll be making use of this particular continuity equation and coming up with the velocity of a overland flow. So we'll be making use of the concept of the fully developed laminar flow down an inclined plane while deriving this. Okay, so further, if you see, so for uniform, so this is we have already seen, and what we'll be doing is for uniform flow. So the so we already said our assumption was uniform flow. So uniform flow we can say S naught, that is the friction, is equal to the friction slope. The bed slope and friction slope will be same for a uniform flow. That will be equal to HF by L, right? So then we can derive, we can further derive this, simplify this. We can compare this with, we can substitute HF by L here. And we can compare this with the Darcy Wabash equation and come up with the relation for the laminar flow, that is the overland flow. This is how it is derived. So the only thing, so the further derivation you can see the lecture. The only thing that you need to remember is that it is assumed as a fully developed laminar flow along a inclined plane. This is something that you need to remember, because similar thing we saw in the previous lecture where we're deriving the flow through the unsaturated zone. So there we assume that the moment for the deriving the momentum equation, we assume that the flow is similar to a laminar flow in a closed conduit, laminar pipe flow in a closed conduit. So similarly, here we are assuming it as a fully developed laminar flow down an inclined plane. Okay, then we are applying the fluid mechanics concept, and finally combining the momentum and this equation, we will be creating the relation. So you can see the option. Also unsteady or turbulent, so this is wrong. Second is fully developed uniform laminar flow in inclined plane. Yes, that is what is used to derive the momentum equation. Flow that is independent of Reynolds number, so Reynolds number and dot we'll be deriving in terms of Reynolds number. You can see the lecture notes. And but this is wrong. It is independent on Reynolds number. So when if the flow becomes turbulent, it becomes independent. When the flow is laminar, it is dependent on Reynolds number. Laminar flow where the friction slope is greatly different from the bed slope. No. So we made the assumption that it is a uniform flow. That's why we said the bed slope is equal to the friction slope. Right. So the correct option is B. So we can move it quickly now. The next question is according to the Horton stream ordering, what is the order of streams when a order two streams join another order two stream? So this is a simple question. So I already showed you what is a catchment. So this is if you take this as a catchment, uh, if this is a catchment, so we'll be having a main stream, right? And we have substreams. So we need to give a stream ordering. So there is a technique defined by Horton stream ordering system. And further we have another streams splitting from this, or maybe like this. So what they are saying, so what we do is basically we will give a number outermost stream, that is the smallest stream, narrowest stream will give number 1. So this is 1, and this is also 1. So these two combine to form this like this. And this will be also 1. 2, what the rule is that 2 I order streams combine to form a stream of I plus 1. A stream I combines with stream I to form a stream of order I plus 1, right? And if a stream I combine with a stream J where I is greater than J, then it will result in a stream of order of the highest order of the individual streams, right? So this is the rule. We can follow this. So here, if you apply that I plus I, it will be forming a stream of I plus 1. This will be 2. And here also we have 1, 1. We have 2, 2 twos will be joining. So it will make 3. This will be 1, 1 with 3. This will be 3. This is 1 and 3. This will be 3. So like that, this is 1, this will be 3, this will be 1, this will be 3. So the stream order will be 3 here. The highest stream order is 3, right? So here the question is two order two streams are joining, right? Two orders two, what is the order of the next? That will be equal to order 3, right? So rest are wrong. So that is the example here. Two orders two streams are joining to make a stream order, new stream of order 3, right? So that is done. The next question, we can move to the next question. So that is, which of the following represent drainage density of the catchment? So there are two things. That is, one is the stream density and another is the drainage density. So you just need to understand what is the difference between both. So two things. One is drainage density, the and the next is stream density. So drainage density is the ratio of, so it is a ratio of length of all stream channels in a catchment divided by the area of the catchment. So the idea is higher, it is just the ratio of length of the all the stream channels. So how many stream channels are there? All the length if we add up divided by the area of the catchment that gives the drainage density. The idea is higher, so higher the DD. So DD is high, more efficient will be the drainage. Higher the drainage density, the runoff will be faster. Yes, faster. Okay, so that is the one thing that you need to remember. And coming to stream density, it is nothing but the ratio of number of streams ns of a given stream order per kilometer square, uh, per kilometer square, per kilometer square. Or you can write, if you want to write it as a fraction, divided by the area of the catchment. Right. So here it is not the length, but the number of streams of the given order by the area of the catchment. That is nothing but stream density. So it is number of streams ns by area. Here will be length of stream ls by area. So you don't get confused with this. Drainage density is the length by area. Stream density is nothing but the number of streams by area. So options are drainage density is the number of streams. So no, it is the number refers to stream density. Then the ratio of total length of all streams by the catchment areas. That is the right option, right? Option B. Yes. The ratio of catchment area to total length, so it is the inverse. That is wrong. The number of stream junctions divided by the main stream length. That is also wrong. So that is the difference of a drainage density and a stream density. So now we have covered the almost all the concepts which was covered in the week 6 lectures. And now we will move on to the numerical answer type questions. Okay. So in this, before the surface water had started, there were some portions taken related to the Green-Abt equation. That is an equation to quantify infiltration rate. That is the cumulative infiltration depth, and the infiltration rate can be analytically found out with the help of the Green-Abt equation, right? So we had already done one question where we assume that the ponding has already occurred and it is at the ponding depth and the ponding depth is negligible. T is equal to at the time of ponding. What is this? So that we had already calculated. But now, when after ponding, how much water will be more infiltrated? That we had seen in the previous week 6 lecture. That is the equation we have derived. And based on that, we will be solving these questions. So the first question is compute the ponding time. So we need to find the ponding time and the depth of infiltrated water uh, at a ponding for a silty loam soil with effective saturation 30%, subject to a rainfall Parts are there. One is 1 centimeter per hour and 5 centimeter per hour. So, and these are the values we need to take consider for a sandy loam soil, right? So we can start solving this. Uh, so we are given with the soil type is silt loam, and for silt loam soil, psi delta theta is given as 5.68 centimeter. The conductivity or the permeability is given by 0.65 centimeter per hour. And one more thing that is given is theta E. That is SC is given, right? SC is given as 0.3. So SE was can be used to find delta theta. We know the relation we had already used in the previous lecture. So if that delta, if the this particular value was not given, psi delta theta was not given. Instead, we were given with the psi value, suction head value, and we could have found delta theta using SE, and we could have substituted here and found psi delta theta. But directly in the question we are given psi delta theta, so XC is not required in this question. Okay, so in all the questions, more all of the data won't be required, so it is up to you to find out which all the data which are required, which are not required. Okay, and we can take the first case now. First of all, we can write the equation for the ponding depth. So if you remember, ponding depth was not the ponding depth, ponding time was calculated as K psi delta theta divided by I into I minus K. So where Tp is the ponding depth, K is the hydraulic conductivity, psi is the suction rate, delta theta uh, is the change in moisture, that is the change in moisture uh, or the moisture deficit. I is intensity of the rainfall, right? So basically, ponding time is nothing but once the rainfall occurs. So the how much time is it takes uh, for the ponding to occur. So it has to satisfy all the losses, and after satisfying all the losses, the ponding starts occurring. That time is called ponding time. And we have derived this equation. If we have the equation, we can do this direct substitution. The first part is when I is equal to 1 centimeter per hour, then dP will be psi delta theta, that is 0.65. No, psi delta theta is not 0.65, it is equal to 5.68 into K, that is 0.65, divided by I, that is 1 minus 0.65. So this will be coming around 10.5 hours. So the key takeaway is that when 1 centimeter per hour rainfall is happening, after 10.5 hours only the ponding will start. Oh, ponding will start after 10.5 hours. And the ponding depth or the infiltration depth that happens, FP, the infiltration depth at ponding will be equal to, if given by I into TP, right? That is up to ponding, whatever the infiltration is, precipitation is happening, that that at that rate infiltration will be happening, right? Till ponding. Ponding will occur only when the rain density crosses the infiltration rate, infiltration capacity, right? So before ponding or till ponding, the intensity, infiltration intensity and the rainfall intensity will be the same. Infiltration capacity, infiltration rate, and the rainfall intensity will be same. So we just have to multiply I with TP, that is 1 into 10.5, that is 10.5 centimeter. And till time of ponding, the infiltrated water depth will be 10.5 centimeter. Fine. So now we can take the second case B, where the intensity is 5 centimeter per hour. So it has increased 5 times higher intensity rainfall is occurring. Then TP, if you substitute, that is 5.68 into 0.565, that is all same. And It is 5 divided by 5 minus 0.65 will be coming around 0.17 hours. That is nothing but around 10 minutes. Right. So earlier it took 10 hours the ponding to start. Now it will take only, if a 5 centimeter per hour rainfall is happening, it will take only zero point 0.7 or 10 minutes to the ponding to start. And the infiltrated depth, so depth of water infiltrated at the time of ponding will be I into Tp, same equation. The intensity is 5 and the hours is 0.717. 0.85 centimeter, and the infiltration depth is only 8.5 centimeters. So two things to take away: when a lower intensity rainfall happens, it will take higher time for ponding, more infiltration will happen. And when high intensity rainfall happens, it will take lower time for ponding and very low infiltration happens. That is the reason why the if you see the floods due to the cloudburst and all, where high intensity rainfall is happening, the time taken for ponding is very less, and also the infiltration is less because most of them are getting converted to runoff. Get the soil gets saturated, top layer gets saturated, and runoff are generated. But for a long, smaller intensity, the time of ponding is more, and the infiltration depth is small. Loss is also more. Right. So through these retention tanks and all, which we discussed in the previous questions, what we are trying to do is to decrease the time of ponding, rather increase the time of ponding. More time to take, so for the water to get ponded on the surface. Right. So we can, so that is it. That's it. We have to round off to the two decimal places. The first answer will be 10.5 hours, and the second answer will be 10.5 hours, and second is 0.17 hours. So that is TP at 1 centimeter per hour, I equal to 1 centimeter per hour, and TT at I is equal to 5 centimeter per hour. So that is the relation of time of ponding if you are given with the soil characteristics like suction head, delta theta, and also the hydraulic conductivity. We can, and if we know the right one intensity, we can find the time of ponding. Right. The next question is calculate the cumulative infiltration. So FP we want to calculate, depth we have to calculate, and infiltration rate, okay, small f also. Both we have to calculate after 1 hour of rainfall. Time is equal to 1 hour of rainfall. Intensity is 5 centimeter per hour. Same silt, long soil. The values are the same. Delta theta is 5.6 and K is 0.65. With an any effective saturation, uh, so effective saturation is 30% for silt and long. So that delta theta is not required. No, SC is not required. We already know delta psi delta theta. So here the time is equal to 1 hour and intensity of rainfall is 5 centimeter per hour. So we already saw the time of ponding for a 5 centimeter rainfall for the silty loam soil given here was equal at 30% effective saturation was equal to 0.17 hours. And after 1 hour, that means the ponding has already occurred. Now they are asking for the infiltration after the ponding has started. After like around 0.17 hours the ponding started, or the first 10 minutes is the ponding started after 10, that is 10 to 50, 10 to 60 minutes, what is the infiltration happening? So that particular equation, that is the infiltration depth after ponding occurs, was derived in the previous week, that is week 6 lectures. And so we know the other terms, delta theta, psi delta theta is given by 5.68 centimeter, and also K is equal to 0.65 centimeter per hour. Right. So TP we already calculated. We don't have to calculate it again. The last question we got it as 1.7 hours. And FP we also, that also we calculated as 0.85 centimeter. Right. FP we got it as 0.85 centimeter. Okay. So that we are not calculating again. And now I will write down the equation, that is when T is greater than Tp, that is after ponding. After ponding, the infiltration equation, that is the cumulative infiltration depth after ponding, that is F. that is minus Fp. F minus Fp is nothing but how much more infiltration has happened after ponding. Minus psi delta theta ln psi delta theta plus F divided by psi delta theta plus Fp is equal to K T minus Tp. Right. So here we can write this as Fv is the unknown that we need to find. Fp we got it as 0.85 and minus psi delta is 5.68 ln 5.68 plus F it is unknown by 5.68 plus 0.85 is equal to 0.65 into 1 minus 0.17, it is equal to 0.54 we will be getting. So we have a nonlinear relation, that is this particular equation. Uh, that is we have F both in the LHS and in the it is like an implicit equation, right? We have F outside here, and then we have inside a radical, that is the ln term we have the F. So we cannot take out F to one particular side and solve it normally. So we have to solve this using numerical technique. So in the last lecture also I showed you a numerical technique that is called trial and error method. Trial and error. It is also called successive substitution. So you can make use of any numerical method, Newton-Raphson method or secant method, any method you can use. So here we will be making use of successive substitution. So what basically we do here is that first we'll make an assumption. So I won't be solving, we don't have much time. So what I will show you the flow, how we do that. First we make an trial for trial 1. We assume value for k. That is F is equal to the first assumption we can give it as KT, K into T. The K is nothing but 0.65 into T is 1 hour, right? That is 0.65. So we can substitute F equal to 0.65. So we can write this particular equation, we can take all this term to the RHS and we can write F is equal to 0.85, we are taking to the other side becomes positive, plus 5.68 inside ln, we will substitute 5.68 plus F as 0.65 divided by 5.68 plus 0.85, that is plus 0.54. This is, if we solve this, we will get a value of F, right? So we will be getting a value of F. Then we will be matching this. That is whether this particular F, if I'm calling this as F, F1, and if we are calling this as F2, this is nothing but F1. We are comparing F1 and F2. So if F2 and F1 are not equal, F2 not equal to F1, we'll make our third guess F3 that is equal to, we'll make calculate our third guess F3 by substituting F as, so basically what we do, we'll calculate F3, that is we'll calculate F3 by substituting by substituting F2, F has F2 that we just found out, and we can repeat this procedure. So when we will be repeating this procedure until we get the two successive f values same. Okay, so finally, if you do this, you can solve it with the help of Excel, or we can try with if any numerical method. We will be getting f as 3.02 centimeter. So we at further iteration we will be getting our f converges to a value of 3.02 centimeter. Right. So you have to keep on substituting this until the previous value and this value is equal to 3.02. Okay. Then we can, if you count the capital F, we can find the small f for the Greenland limitation that is given by this particular formula, that is capital small f is equal to capital F psi delta theta divided by f plus 1, that is will be equal to 0.65. Psi delta theta is 5.68 divided by f is 3.02 plus 1, that is equal to 1.87 centimeter per hour. So the depth is 3.02 and the infiltration rate is 1.87. So at time of bonding, the infiltration depth is 0.85 centimeter, right? That we got. So after 1 hour, infiltration depth is 0.02 and the rate became 1.87, whereas the rainfall is occurring at a rate of 5 centimeter per hour. Okay, so we can move to the next question. So, a catchment is experiencing a 5-hour storm. The rainfall hydrograph is recorded at a local station. So, 5-hour storm is happening. So, rainfall hydrograph is recorded at the local station, providing a successive depth of 1 hour interval. The depths are these. The five values are there. If the direct runoff from the storm is measured to be 55 centimeters mm, so the runoff, the storm has occurred, and at the outlet point, the runoff has been measured as 55 mm. Calculate the phi index for the catchment. So we need to understand what is a phi index first, right? So the question is, there's a catchment and a 5-hour storm has occurred, and the water through the streams have reached the outlet point, and we this is the gauged catchment, and we know the at the outlet point the runoff was measured up to 55 mm, and the inflow was the rainfall density was 55 plus 35 plus 50 plus 25 plus 10, right? So we need to find the phi index. So phi index, so what is a phi index? Phi index is a constant rate of abstraction, that is can be infiltration and other losses like other abstraction losses, other losses. Okay, so runoff during this the time interval when rainfall intensity is strictly greater than the phi index. So constant rate of abstraction is defined as the phi index. The constant rate of abstraction, there's a rate of extraction that is happening at a constant, that well particular value is defined as phi index. So we can write our total runoff minus summation of I minus phi into delta t to make convert the rate into centimeters. So for all interval where t is greater than, where I is greater than 5. So if I could draw the hydrograph, so there are values 15, 35, 50. So initially it was 15, then became 35, then it increased to 50, then it became 25, finally it became 10. So this is the rainfall hydrograph. So abstraction is nothing but a fixed range we will assume. So one is in 1 hour interval. So let us assume, so this particular values I will write here. The values are 15, 35, 50, 25, and 10. So first let us assume that the phi value, first the phi value is less than the smallest uh, small of less than all the rainfall intensities for each interval. All the five intervals is less than that. For all I is less than all I. So like if I'm considering this particular case, so that is why I'm calling it as phi 1. Right. Then let's write this particular equation. Then that is 15 minus 5 plus 35 minus 5 plus 50 minus 5 plus 25 minus 5 plus 10 minus 5. So these differences, that is this particular shaded region. So this will be contributing to runoff, right? These are the abstractions. So these are the abstractions in the below side. Then these will be contributing to the runoff, right? So we can check that if we can equate it, right? We can equate it to total runoff that is equal to 55. So all we have to multiply with delta T, that is 1 hour. So finally we will be getting 135 minus 5 psi is equal to 55, and psi we will be getting as 16 mm per hour. But our assumption was, we'll check whether our assumption was right or not. This is 5 1, 5 1, 5 1, 5 1, 5 1. We took 5 1 is less than, is between. The first assumption was is less than 10 mm. But we are getting it as 16. So our assumption is wrong, right? It is not less than 10 mm per hour. So that was wrong. So in the second trial, we'll make another assumption. Like we know it is greater than, we'll assume the second assumption will be it is between 15. So we can go a step further. So we can make a, well, so it was coming out as 15, right? So we can make a guess it is somewhere here. So psi psi 2 is less than uh, 25, and psi 2 is between 25 and 15, we can write less than 15, less than, here we can like 0 less than, like that, say psi 2 less than 25. Between 0 and 25 is the next assumption. So if it is between 0 and 25, so whatever the excess will be here for the first term, first 1 hour term, there won't be any excess because all are lost as abstraction. I will make the another shaded region. So this is the shaded region. Now that contributes to runoff, right? So that can be written by 35 minus 5 plus 50 minus 5 plus 25 minus 5 is equal to 55. So if you solve this, we'll be getting as 35 110 minus 35 is equal to 55, and 5 you will be getting it as 18.33 mm per hour. Now we can check this 5. This is 5 2, 5 2, 5 2. Second assumption, two cents of second assumption, 5 2. So 18.33 mm per hour is greater than 15, right? It is greater than 15, and also it is less than 25. So our assumption is correct. So the psi value we are getting in as psi is equal to 18.33 mm per hour. So this is the constant rate of abstraction. So at this particular rate, abstraction is happening, right? So all other, so psi 2 is correct. That is 18.33. So the runoff contribution will be the one which I marked in gray portions here, right? So this is how with trial and error we find the value of psi if we know if it is a gauged station and we know the runoff of the outlet. Okay, so we can move to the 10th question. It's a direct question that is it's based on the runoff coefficient. So runoff coefficient is nothing but runoff coefficient C is defined as total runoff divided by total rainfall. So they have been asked in the previous question, the storm which we solved in the previous question, what is the runoff coefficient? So that is very much simple. So we know the total rainfall that happened is 15 plus 35 plus 50 plus 10 uh, divided by total runoff. So it is the inverse. So sorry, so it will be total runoff, that is 55, that is given, and this sum 50 plus 10 plus 25, one more storm was there. This sum will be coming around 135. So that is 55 by 135, that is around 0.4774. So, so how this is the runoff coefficient is coming as 4.4%. So what we do is that we measure the rainfall and runoff of the outlet, and we find the runoff coefficients for that particular catchment or referred watershed. So once we have this runoff coefficients derived with the previous data, whenever rainfall happens, we use this particular runoff coefficient. We multiply the rainfall with this particular value, and then we will be getting the runoff. That is another way of finding the rainfall excess or runoff. Okay. So we can move to the 11th question. So a small catchment is subjected to a severe steady rainfall of constant intensity. So a rainfall is occurring at a constant intensity of 20 mm per hour, which lasts for 2 hours exactly. So intensity we have, that is 20 mm per hour, and it lasts for t is equal to 2 hours. Infiltration characteristics of the catchment soil were described using Horton's equation. So Horton's equation, I hope you remember, we have already derived Horton's equation. We have already seen it's an empirical equation that assumes that the infiltration starts with the initial values F naught, it will be high, then it will decrease exponentially and then reaches a constant value that is called the FP, right? The constant FC, that is called the constant value infiltration. or steady infiltration rate. So that is how Horton's equation is derived. It's an exponential decay, we say. The initial infiltration is given, that is 12 mm per hour. So initially it was this, then it exponentially decreases and reaches the steady state, that is FC, that is 3 mm per hour. The infiltration decay constant is 2 hours. The K, the decay constant is given by 2 per hour. And assume that the all rainfall is not infiltrated, becomes direct runoff. So essentially we are neglecting the abstraction losses like the interception losses or the depression losses or depression storage, that we are neglecting this particular technique, and calculate the depth of rainfall excess or direct runoff in mm generated in 2 hours. So basically what they are saying here is that we have precipitation with us, right? So we need rainfall excess of PE or runoff we want. That is basically they're saying we have to infiltration we have to subtract, right? And we also have the abstraction losses. That is initial abstraction, depression storage. So this will be, if I could mention everything here, then it will be like interception losses, depression storage, and they are assuming that these all are, they're asking us to neglect all these depression strategies are neglected. So if we have the precipitation with us, if we subtract the infiltration that or the infiltration depth that we quantify, we'll be getting the rainfall excess. This is also one method to find the rainfall excess, basically with the using the infiltration equations. Okay, so basically we have the Horton's equation. So I hope you remember the formula. This is an empirical equation that has been derived by Horton, and it is given by F. Infiltration rate at any time t is given by F naught plus F naught minus Fc into e raised to minus kt. Right. So we have the value. So we need to find, if we want to find the capital F, we have to integrate it with respect to time. Capital F, the infiltration depth at any time, is given by F naught minus Fc into e raised to minus kt dt. Right. So we can substitute the values. So F will be equal to 0 to 2 hours. F naught is initial infiltration rate is given as 12 plus 12 minus 3. So 12 minus 3. 3 is the infiltration capacity, constant rate infiltration. So 12 minus 3 will be nothing but 9, right? 9 e raised to minus k is 2, 2t dt. So this will be 12t, that is within the limit 0 to 2, plus 9. So there is a small mistake. So basically it is not F naught, it is FC here. So it is FC. So here it will be 3, not 12. Here also it will be 3, 3t into, from the interval 0 to t, and 9 e raised to minus 2t by minus 2. Here also within the limit 0 to 2 we have to give. So if we give the limit 0 and mention it as a single limit, for t equal to 2 it will be 6 minus, this will be 4.5 e raised to minus 4, that is minus t equal to 0 will be 0 minus 4.5 e raised to 0. So this will be coming out to be 10.41758 mm. So this is the total infiltration depth that has occurred. Okay, and the intensity, total intensity of rainfall I is given the question as 20 and it is remaining constant for the or exactly for 2 hours. So total infiltration is 20 mm per hour. The total precipitation happening is 20 into 2, that is 40 mm, right? So total infiltration will be, so the rainfall excess can be calculated as P minus total infiltration that has happened, F, that is equal to 40 minus 10.4178, 758, that will be coming around 29.582. So if you have to round off to two decimal places, will be 29.58 mm. So that is the depth of runoff that will be happening. Okay. So basically what we did here is, so we have the infiltration equation. So we have a constant rainfall happening at 20 20 mm per hour, right? So this is intensity 20 mm per hour, and this is time for 2 hours, and we have the infiltration rate at starting at 12 mm per hour, and it decreases exponentially and reaches a constant value of this will be 3 mm per hour. Here, what we just did, we found out this particular area that is the infiltration depth after 2 hours. We calculated this as 10.4142 mm, and we subtracted with the total precipitation and we got this particular area that is nothing but the runoff or the rainfall excess. This particular area, we got this as the runoff excess or rainfall excess or direct runoff as 29.58 mm. Okay, so we can move on to the final question. So that is related to the SCS method. So SCS, we already saw the theory, how they are derived. So we can directly go to the numerical. Uh, in the SCS method, compute the runoff for 5 inches of rainfall. So rainfall is given in 5 inches over 1,000 acres of watershed. So watershed area of the Kashmir area is 1,000 acres. And the hydrological soil groups. So different, so I already mentioned we need the recessive retention. Recessive retention is calculated from curve number. Curve number are derived for different classes of, it depends on soil groups. There are three types of groups, group A, group B, and group C. So they have mentioned that hydrological soil groups have 50% B group and 50% C group. So out of the 1,000 acres of land, 50% of this, that is 100 or the 500 acres of land has Group B soil and 500 acres of land has Group C soil, uh, interspread throughout the water catchment. Anderson moisture condition is assumed to be 2. So AMC category is 2 and the land use is, so if you see the land use, it has 40% residential area with 30% imperviousness, 12% residential area, 65% imperviousness, and 18% paved road with curbs and stumps, 16% open land with 50% fair grass cover, and 50% uh, grass cover with 14% parking lot schools. All are impervious. So this will be like a practical problem that will be given to you. That is that will be having all the characteristics of the catchment that you have been derived. So here we need to come up with the curve number. Once we have the curve number, we can directly substitute to find the rainfall excess, right? So we can write the formula once. That is rainfall excess P is given by PE is given by P minus 0.2 S the whole square divided by P plus 0.8 S, right? So the only issue is finding S. So S, it has can be a function of curve number, right? So curve number relation we found out as 1000 Cn by 10. That no, S is equal to 1000 Cn by 10. Cn by 10, where we want S in inches. So our question is in inches. So we can use this particular equation, right? So we need to find what is the curve number this for this particular location. So here we can make a table. So the table will have land use, which we can write the hydrological soil group. So we have group two types of soil, group B soil and group C soil, right? There are two types of soil, and within that we can make the column for percentage percentage area, corresponding curve number, and the product. Product I'm denoting by X. And then we have the percentage area, we have the corresponding curve number, and we have the product. So basically we are finding the weighted curve number so that we can substitute that and find the specific retention of that surface, right? The first land use is residential area. I'm writing it as R with 30% imperviousness. And so how much area is that? If you see the question, 40% of the residential area, that is 30 with 30% perviousness. So total 40% uh, of the residential area, 40% of the area is residential area, right? And there are two classes of soil. So we have to distribute this 40% to each of the soil classes. So the percentage will be total 40. So it will be 20 in class B and 20 in class C for group C and group E, right? So 20 here and 20 in C, right? And Cn for that we can find from this particular table. From this particular table, we know we are looking for group B and C. So these are the values that we are looking into. And for a residential area with the imperviousness of 30%, so we have the values as 72 and 81, right? So we can write down that value 72 and 81. And this product we can take, that is 1440, 20 into 81 is 1620, right? Similarly, for residential area with 65% imperviousness, total is 12%, so it will be distributed as 6%. And from the table, you can find those values as uh, with 65% perviousness, it is 85 and 90, right? This was the first value that we took. This is the second value, that is 85 and 90. So we can write down those values. It is 85 and 90. So the sum will be given 510 and 540. Right. Similarly, we can write for the others, that is Next line uses roads. For roads, the total percentage of roads is paved roads of 18 percentage paved roads. So we can distribute it as 9, 9. And the curve number for paved roads is equal to, if you see if for the both the cases, the curve number is equal to 98. So we can substitute 98. 98, 98, the product will be 882. The product is just to simplify 882, 882. Next is the open land. So you can follow the same procedure. So I'm writing down the good cover and fair cover. There are two types of overland, that is open land with good cover classification and fair cover classification. Those values we can take out from the table, and one for good cover and for uh, fair cover, and it will be open land, which will be coming around total 8% 4, and the curve numbers are 61 and 69. This we can get from the table. 244 and 276 will be coming around, and similarly here it will be 74 and 79, 9 will be 296 and 316. Okay, and finally parking lot, etc. will be 7, 7, 14%. So we're distributing a 7, 7, and our number is 98. Here also 98, it will be 686. This also will be 686. So we can do a check. If you sum it, you have to get 50 here. Here also you have to get a 50 here. Total should be 100%. And this product sum you have to take, that is for 4048. And this product will be sum will be 4340. So these are the two values we will be need to get out of this particular table. So weighted curve number is next. So we need a single curve number. So weighted curve number Cn will be equal to 4038. These both are in percentage. 4340 divided by 100. That will be equal to 83.8. Right. The weights will be 50%. Right. Zero point 0.5 into 0.5. That is. Hmm. So we got the curve number. So we can substitute that to find S. So S will be 1000 by curve number, that is equal to 83.8 minus 10, that will be equal to 1.93 inches. We will be getting it as inches, right? And when if you got that in inches, we can substitute this. PE rainfall excess is equal to minus 0.82 or 0.2 into 1.93, the whole square, divided by P plus 0.8 into 1.93, that we'll be getting. P is nothing but 5, so we'll be getting it as 3.25 inches. So for the rainfall of 5 centimeter per hour, which 5 inches, that total depth of 5 inches that happened in this particular catchment which had these properties, the total runoff that will be generated by SCS curve method is equal to 3.25 inches. Okay, so I'm concluding this here. So if you have any further doubt in this particular questions or any other assignment questions, you can contact me. My name is Akhil J. My email ID is AKHILJNANADEVAN at gmail.com. So thank you for attending my section. So we'll be meeting again next week with the week 7 problem solving section class. Thank you.